So this is number theory lecture 3, and according to the syllabus, what I'm doing this morning is review, which means answering questions about the division algorithm and the greatest common divisors and working problems. So I did a few problems from section 1.1. Maybe I'll start with section 1.2. And exercise 1 is to compute the greatest common divisor of these two numbers, 935 and 1122. When you put two numbers in parentheses separated by a comma, this means greatest common divisor. Let's see if I can get this whole page on the screen at once. Greatest common divisor. So one way is just a kind of trial and error, I guess. What numbers could divide both of these? Well, 1122 is even, but 935 is not. So 2 doesn't divide both of the numbers. If you check, 3 divides 1122, but it doesn't divide 935. So 3 is not a common divisor. 5 divides 935, but it doesn't divide 1122. So 5 is not a greatest common divisor.
Professor.
Yeah.
It's not easier to find the prime factorization of each one, and then when we have the factors, we can look at like the highest number we could get in common.
We can try that. For example, 5 certainly divides 935. So if you divide 5 into 935, that goes 187 times. 187, let's see, it's not divisible by 235. It is divisible by 11. So 935 is 5 times 11 times 17. So if we factor this number as much as we can, this is what we get. Huh. What about 1122? Well, if we divide 1122 by 2, we get 561. If we divide 561 by 3, we get 187, which we already saw is 11 times 17. So this says 561 is 2 times 3 times 187.
So that's the largest common divisor, right?
So this says that 187, well, let's just do it like this. 935 is 5 times 187. It should have been 1122. 1122 is 6 times 187. And 187 is a common divisor, and it's the greatest common divisor. So the greatest common divisor of 935 and 1122 is 187. At least this is one way to do the problem, right? And there are more efficient ways to do it. On the next, remember, next week, there's no class Monday or Wednesday, so we have no lectures next week. But a week from Monday, which is the 4th lecture, we'll learn the Euclidean algorithm, which is an efficient algorithm to compute greatest common divisors. But this method of just trying to factor by hand with relatively small numbers, often, not always, it often works. And what's nice about this is you get to play with numbers. And in number theory, it's good to have numbers. Any questions about this? So this is exercise 1. What about exercise 2? Let me keep doing some greatest common divisors. Let's see. So this is still section 1.2, exercise 2. And here we want to compute the greatest common divisor of 3 numbers: 168, 252, and 294. And the first thing we see is that each of these is even. So 2 is certainly a common divisor. 168 is 2 times 84. 252 is 2 times 126. 294 is 2 times 147. Now, these 3 numbers, 84, 126, and 147, they're not all even, so 2 doesn't divide.
Child, we got 3 kids on the bus.
So 2 divides all 3 of these numbers, but 4 does not. 4 doesn't divide 294. But let's look at these 3 numbers. Are they divisible by 3? So 84 is 3 times 28. 126 is 3 times 42. 147 is 3 times 49. So 3 divides these 3 numbers, so 3 also divides these. And if you look at 28, 42, and 49, you might recognize that each of these numbers is divisible by 7. That is, 28 is 7 times 4. 42 is 7 times 6. 147, 49 is 7 times 7. So we have 168 is 2 times 3 times 7 times 4. 252 is 2 times 3 times 7 times 6. And 294 is 2 times 3 times 7 times 7. 2 times 3 times 7 is 42. This is 42 times 4, 42 times 6, 42 times 7. And the greatest common divisor of these 3 numbers is 42. Each of them is divisible by 42. And if you divide by 42, you get 4, 6, and 7. And the greatest common divisor of 4, 6, and 7 is 1. Right? There's no common divisor of these other than 1. Okay. Any questions about this? Let's see. What about exercise 4? You want to find 4 relatively prime integers, positive integers, let's say, such that no 3 of them are relatively prime. So you want to find A, B, C, and D, and any 3 of them have a prime in common, but the 4th doesn't. So let's say maybe A is 2 times something, B is 2 times something, C is 2 times something, but D isn't divisible by 2. Suppose each of these numbers, so each of these numbers except D is divisible by 2. Suppose I want each of these numbers except C to be divisible by 3. So I could multiply, put a 3 here. Let's take another small number like 5. Suppose I want each of these numbers except B to be divisible by 5. And suppose I want all these numbers except A to be divisible by 7. So then this number is 30. This is 42. This is 70. And this is 105. So these 4 numbers, for these 4 numbers, the greatest common divisor of all 4 of them is 1. But the greatest common divisor of A, B, and C is 2, bigger than 1. The greatest common divisor of A, B, and D, is 3. So leave out D, leave out C, leave out B, A, C, and D. The greatest common divisor of A, C, and D is 5, which is bigger than 1. And if I leave out A, the greatest common divisor of B, C, and D, these are all divisible by 7. So here, it's a miracle. I was able to write down 4 positive integers that together had no common factor. These 4 numbers are relatively prime, but every choice of 3 of them does have a common factor, a common divisor greater than 1. So no 3 of these numbers is relatively prime, but the 4 of them are. So this is just a cute example. All right. Oh, these are fun. Let me keep doing some more of these problems. Let's look at exercise 7. In section 1.2, we were assigned 1 to 10. What about 7? Prove that the numbers 3n plus 2 and 5n plus 3 are relatively prime for all n. So it's always good to do some experiments Let's just make a table. N, 3n plus 2, 5n plus 3, and the greatest common divisor of 3n plus 2. Let's look at the first 5 cases. When n is 0, 3n plus 2 is 2, 5n plus 3 is 3. Greatest common divisor of 2 and 3 is 1. When n is 1, 3n plus 2 is 5, 5n plus 3 is 8. The greatest common divisor of 5 and 8 is 1. What about n equal 2? 6 plus 2 is 8. 10 plus 3 is 13. The greatest common divisor of 8 and 13 is 1. What about n equal 3? When n is 3, this is 9 plus 2 is 11. This is 15 plus 3 is 18. Greatest common divisor of 11 and 18 is 1. What about n equal 4? 3 times 4 is 12, plus 2 is 14. 5 times 4 is 20, plus 3 is 23. And the greatest common divisor of 14 and 23 is also 1. Okay, so this is just that. This is, you might call this experimental data, right? Sometimes people think that only biologists and chemists and physicists do experiments, but number theorists, mathematicians do experiments. They look at numerical cases. So for these first 5 cases, this statement is true. So this gives us some confidence that maybe this really is correct. So let's see, how can we prove this? Well, let's recall the following. So we proved in the lecture on Monday the following theorem. This was theorem 1.4. If you take any set of integers, and here I'm just taking 2 integers. So if the GCD, if the greatest common divisor of A1 and A2 is equal to D, then there exist integers x1 and x2 such that a1x1 plus a2x2 is equal to D. And if you have such a relation, you see that every common divisor of A1 and A2 does divide D. And there was a corollary of this, which is theorem 1.4. In the case when you only have 2 numbers, it says A1, A2, these integers are relatively prime if and only if there exist integers x1 and x2 such that a1x1 plus a2x2 equals 1. So if we want to apply this to these two numbers, 3n plus 2 and 5n plus 3, 3n plus 2 and 5n plus 3, these are relatively prime if and only if you can find integers. Let me call them, instead of x1 and x2, let me call them x and y. 3n plus 2x plus 5n plus 3y equals 1. Can we solve this equation in x and y? Let's see. If we rewrite this, this is 3nx plus 2x plus 5ny plus 3y equals 1. I have two terms that involve n. I have 3x plus 5y times n plus 2x plus 3y equals 1. Now, suppose I could find x and y such that this is equal to 0 and this is equal to 1. That is, suppose I could find x and y such that 3x plus 5y equals 0 and 2x plus 3y equals 1. Well, now this is reduced to high school algebra. This is two equations and two unknowns. And you should know how to solve that. So I'll leave it to you to solve it. I'll just tell you what the unique answer is. If you take x equal minus 2 and y, sorry, if you take x equal minus 3 and y equal 2, this is solved. Which means for any n, if I take minus 3 times 3n plus 2 plus 2 times 5n plus 3, I have minus, oops, sorry, I did something wrong here. Let me just double check. 3x plus 5y equals 0. So x equal minus 5. Right, if I want to solve these two equations and two unknowns, if I let x equal minus 5 and y equal, oops, x equal 5 plus 5 and y equal minus 3, that solves these equations. 15 minus 15 is 0. 10 minus 9 is 1. So 5 times 3n plus 2 minus 3 times 5n plus 3. What is that? That's 15n plus 10 minus 15n minus 9 is 1. So I have something times 3n plus 2 plus something times 5n plus 3 is 1. That means that these two numbers are relatively prime. So that's a proof.
So, Professor, can I ask you a question?
Yes.
So as long as you have two numbers which you can use to do a linear combination and show that is equal to 1, that's good enough, right? With at least two numbers, correct?
So in this problem, we want to show that for any n, the two numbers 3n plus 2 and 5n plus 3 are relatively prime. And one way to do this there can be another way, but one way to do this is to find numbers, here I call them x and y, such that x times 3n plus 2 plus y times 5n plus 3 equals 1. And if that's the case, any common divisor of 3n plus 2 and 5n plus 3 must divide 1, and the only numbers that divide 1 are plus or minus 1. So they are relatively prime. Does that answer your question?
Yes, but what I'm saying is with just one pair of x and y, that's good enough, right?
Yeah, sure.
Thank you, Professor.
Yeah. Yeah. Let's go back to section 1.1. Let me do some of the problems there. Does anyone have a particular problem you would like to see me do right now?
Yes, for homework one,
Sorry?
for homework one, can you do number 8?
Okay. Number 8 says, prove that if n is even, then n squared is divisible by 4. So prove. If n is even, what does that mean? It means n is a multiple of 2. N equals 2 times d for some integer d. So n squared is the quantity 2d squared, which is 4 times d squared. So n squared is 4d squared. So 4 divides n squared. That's the whole proof.
So the first step is the base case. So the
No,
first
this is
line,
not an induction. There's no base case. This is just a
okay.
just a direct proof.
No, I'm very new with those things. So what kind of step you use to demonstrate? Because I'm learning the induction method right now.
I'm sorry. Yeah, the sound on the internet here is a little bit garbled. So could you just repeat again what you said?
Yes, I'm using the induction method right now because I'm very new to write like that. So, what kind of strategy do you use to develop?
So you're saying, can I prove this by induction?
Right.
Okay, so here's an alternate proof by induction. So we could look at the case n equals 0. In that case, n squared is 0 squared is 0, which is 4 times 0. So n squared is divisible by 4. Or if you want to start with n equal to, n is even, n equal to 2. 2 squared is 4, which is 4 times 1. So, or actually, let me do it slightly differently. So suppose we let n equal 2k. So when k is 0, n is 2 times 0 or 0, and n squared is 0 squared, which is 0, which is 2 times 0. So In this case, when k is 0, n squared is divisible by 2. And when k is 1, n is 2 times 1, which is 2. So n squared is 2 squared, which is 4. Sorry, 0 is 4 times 0. N squared is divisible by 4. When n is 2, 2 squared is 4, which is 4 times 1. So again, when k equals 1, the number 2k is divisible by 4. So suppose 2k squared is 4 times something, 4d, well, let's say 4q. Then what can we say about 2 times k plus 1 squared? So this is 2k plus 2 squared. So this is 4k squared plus 8k plus 4. 4k squared is 4q, and this is 4 times 2k plus 1, which is 4 times q plus 2k plus 1. So if the square of 2k is divisible by 4, the square of 2 times k plus 1 is divisible by 4. So this is, if you like, a proof by induction, but it really is a terrible proof compared to doing it the first way, which is much cleaner and simpler. So this is correct, but this is correct. If you do this, you get full credit. It's just not as nice as the earlier proof because we try to make things as easy as possible. And this first proof is much easier. Right.
So what is the name of that?
It doesn't have the name of this. It doesn't have a name. It's just a proof. It comes from thinking. You know.
Yes, but I'm saying the first step you compute to prove it is true. Because it is true, so I can demonstrate further. But
You mean in this?
right.
Well, this is a proof by induction, but it's really not. It's not a.
Effective.
It's a proof you should avoid if you can do it in an easier way.
Okay.
But if you want to
Okay.
use this, the method is induction. So it's induction if you want a name for it, but this is not induction. This is just a direct proof.
Okay, thanks.
So, Professor, since you said the first one is a bit more elegant, and it is because I did the second version, would we be penalized for not being able to? do the
Absolutely
first
not.
one?
If I
Okay.
ask you for a proof and you give me a proof that's correct, whether it's long or short or aesthetically pleasing or not, any proof that's correct is full credit.
Roger, thank you.
You know, I mean, if you solve the problem, you solve the problem. You get credit. Doesn't matter how you do it.
Professor, can you do number 7 from the homework one?
Yes.
Yes.
So number 7 is to compute the 100-adic representation of the number 783,614,955. So this is M-adic with M equal to 100. So, or 10 squared. M squared is 100 squared, or 10 to the 4th. M cubed is 100 cubed, or 10 to the 6th, and so on. Let's see. So what is this number? This is 700, this is a million. M to the fourth, which is 100 to the fourth, that's 10 to the eighth. Ten to the eighth is 100 million. So what is this? 614. Sorry, 783,614,955. So what's the largest power of 100 less than or equal to this number? So this is greater than 10 to the eighth, because this is 100 million, and this is over 700 million. So this is less than 100 to the fourth. This is greater than 100 to the fourth, and less than 100 to the fifth. M to the fifth, which is 100 to the fifth, is 10 to the 10th. This is 10 billion. This is less than 10 billion. So 783,614,955. This is 700 million plus 83,614,915. This is 700 million. That's 7 times 100 to the fourth. That's what that is. What is, let's look at 83,614,915. This number is between 1 million and 100 million. So 83,614,915 is 83 million plus 614,915. This is 7 times 100 to the fourth. This is 7 times m to the fourth. And m is 10 squared. $83 million. This is 83 times a million. A million is m cubed plus 614,915. 614,915. This is less than a million, but bigger than 10,000. This is 610,000 plus 4,915. This is 61 times 10,000. That's 61 times 100 squared. So since these numbers are sort of flying all over the place, let me just repeat what I just did to make so it's clearer. We want to find, we have m equal to 100, and we want to find the m-adic representation of this number, 783,614,955. So we want to write this as A0. So the digits are, the A sub i's are between 0 and less than 100, between 0 and 99. So I want to write this as A0 plus A1m plus A2m squared plus A3m cubed plus A4m to the fourth, right? If m is 100, m to the fourth is 100 to the fourth. What's 100 to the fourth? That's 10 to the eighth. That's 100 million. So this number is bigger than 100 million, but less than 100 times that. So this number is going to have an M-adic representation when m equals 100 of this form with these coefficients. So let's try and work that out. So m is 100. The number 783,614,955. What is this equal to? This is 83,614,955 plus 700 million. That's 83,614,955 plus 7 times 100 million. 100 million is m to the fourth. (100 to the fourth). What's 100 cubed? That's a million. This is 83 million. No. Let me write it like this. This is 614,955 plus 83 million plus 7 times 100 to the fourth. A million is 100 cubed. This is 614,955 plus 83 times 100 cubed plus 7 times 100 to the fourth. What's 100 squared? 100 squared is 10,000. This is 610,000. All right, let me write it again the other way. This is 4,955 plus 610,000 plus 83 times 100 cubed plus 7 times 100 to the fourth. This is 4,955. This is 61 times 10,000 times 100 squared plus 83 times 100 cubed plus 7 times 100 to the fourth. 100 to the first power is 100. This is 55 plus 4,900 plus 61 times 100 squared plus 83 times 100 cubed plus 7 times 100 to the fourth. So this is 55 times 1, which is 100 to the 0. This is 49 times 100 to the first power plus 61 times 100 squared plus 83 times 100 cubed plus 7 times 100 to the fourth. And this is the answer. When you expand this number to base 100, the 100 adic representation is this. And these are the digits. The digits have to be between 0 and 99. And here they are, 55, 49, 61, 83, and 7. All right, well, take a minute and think about that, because it's just arithmetic, right? This is not very sophisticated abstract mathematics. This is just arithmetic, but very few people have ever done arithmetic. It doesn't use anything that you don't learn in elementary school, except at a much higher level. But you don't need calculus, you don't need differential equations, you don't need linear algebra to do this. You just need to do arithmetic. Okay. Any questions about this? Okay.
Professor.
Yes.
I have a question regarding the due times of the homeworks. And the PDF, it says some different dates from the Blackboard assignment. So the date that we will follow as a due date will be the one in Blackboard.
So what is on the, here, this is the schedule of homework,
Yes.
but where it says homework, this is not the date that it's due. This is the homework that covers the material in this section. So for
Okay.
section 1.1, the homework is this, but the due date is on Blackboard.
Okay, perfect. Thank
Okay.
you, Professor.
Like, for example, on Monday, I talked about greatest common divisors. You couldn't turn the homework in on Monday. The homework is due whenever it's due, in about a week and a half, I think. So the due date is on Blackboard. These are just the homework problems associated with the lecture for that day. And today, it says review. This is just means I'm going over problems from the first two lectures. Okay. Let's see, what are some other problems I might do? What about problem 9? This is still section 1.1. Prove that if n is odd, then n squared minus 1 is divisible by 8. And again, let's just do a little experiment. Suppose I make a table, n squared minus 1. So if n is 0, sorry, n is odd, so n can't be 0. Suppose n is 1, 1 squared minus 1 is 0, is divisible by 8. It's 8 times 0. If n is 3, this is 9 minus 1 or 8, which is 8 times 1. If n is 5, 5 squared is 25 minus 1 is 24, is 8 times 3. If n is 7, 7 squared is 49 minus 1 is 48, which is 8 times 6. If n is 9, 9 squared is 81 minus 1 is 80, is 8 times 10. If n is 11, 11 squared is 121. 121 minus 1 is 120, which is 8 times 15. If n is 13, 13 squared is 169. Minus 1 is 168, which is 8 times 21. If n is 15, 15 squared is 225 minus 1 is 224. If you divide 224 by 8, you get 8 times 28. Oh, it's fun. Let's do one more. 17. 17 squared is 289. Minus 1 is 288. That's 8 times 36. So at least for n equal 135 up to 17, these first 8 odd numbers, this is correct. But that's not a proof, that's just experimental data. You don't have to do this, but it's nice to do it just to see what's going on. So, but how do we do the proof? If n is odd, that means n is 2k plus 1 for some integer k. So n squared is 2k plus 1 squared, which is 4k squared plus 4k plus 1. So n squared minus 1 has the form 4k squared plus 4k. If I factor out the 4k, I get 4k times k plus 1. And for any integer k, k times k plus 1 is even. Because either k is even or k is odd, but then k plus 1 is even. So k times k plus 1 is 2l for some integer l. So therefore, n squared minus 1, which is 4k times k plus 1, k times k plus 1 is 2l. That's 8l. So n squared minus 1 is a multiple of 8. And that's the proof. 8 divides n squared minus 1 for every odd number n.
Professor, why you call data? Because
Why did I
like
call it
facts.
data?
Yes, I mean.
It's
like-
data. It's information.
Oh, okay.
It's facts. I mean, it's whatever you want to call it. It's just examples. Anything you want to call it is okay. Right? But this is an example of a proof. It's an elementary proof. And this is the kind of thing you have to be able to do in a mathematics class. So the last problem I did with the 100-adic representation, that was a calculation, not a proof. This is a proof. And you have to be able to calculate and you have to be able to prove things. Right. Any questions about this?
Professor,
Yeah,
can you do number 8 in section 2?
section 2, number 18,
No, number 8.
number 8.
Yeah, with the factorials.
Okay. Let's take a look. So this is section 1.2, exercise 8. Prove that n factorial plus 1 and n plus 1 factorial plus 1 are relatively prime for every positive integer n. Well, again, let's just do some experiments. So for n, here I'll write n factorial plus 1, and here I'll write n plus 1 factorial plus 1. So when n is 1, and you remember, you know n factorial is the product of all the positive integers up to n. And if you needed to define 0 factorial, we don't have to in this problem. 0 factorial is defined to be 1. So when n is 1, n factorial is 1. This is 1 plus 1, or 2. This is, when n is 1, n plus 1 is 2. This is 2 factorial plus 1, which is 2 plus 1, which is 3. And the greatest common divisor of 2 and 3 is 1. So this is okay. What about when n is 2? 2 factorial plus 1 is 3. What is 3 factorial? 1 times 2 times 3 is 6, plus 1 is 7. And 3 and 7 are relatively prime. What about when n is 3? 3 factorial plus 1, we just saw was 7. 4 factorial plus 1. What is 4 factorial equal to? Can someone tell me?
$24.
Yeah. 4 times 3 times 2 times 1 is 24 plus 1, which is 25. And the greatest common divisor of 7 and 25 is 1. Let's do one last one. 4, n equal 4. 4 factorial plus 1, we just saw was 25. 5 factorial plus 1. 5 factorial is 120, plus 1 is 121. And the greatest common divisor of 25 and 121 is also 1. So at least for very small values, this is true. So the question is, why is it true in general? So let's see. Let D be a common divisor of n factorial plus 1 and n plus 1 factorial plus 1. So again, n factorial is the product of the numbers up to n. N plus 1 factorial is the product of the numbers up to n plus 1. This is n factorial, so n plus 1 factorial is n factorial times n plus 1. So if D is a common divisor of these two numbers, suppose we let n factorial plus 1 be equal to d times q? What can we do? I don't know. Anyone have any suggestions?
I'll be honest. No.
Well, let's see. So I don't know. What can we do? N plus 1 factorial is n factorial times n plus 1. So n plus 1 factorial plus 1, that's n factorial times n plus 1 plus 1. I can write that as, so n factorial, I'm going to write that as n factorial plus 1 minus 1. That's okay, because 1 minus 1 is 0, times n plus 1 plus 1. So that's equal to n factorial plus 1 times n plus 1 minus n plus 1 plus 1. So this looks like n factorial plus 1 times n plus 1 minus n. And n factorial plus 1 is d times q.
Professor, can you raise the paper, please?
Sorry?
Raise the paper a little bit.
I'm sorry. I didn't hear what you said. Could you? The audio is a little garbled here.
I can see the bottom part.
I will start it on a clean page. So we want to show that n factorial plus 1 and n plus 1 factorial plus 1, the greatest common divisor is 1. Okay, that's what we want to prove. So suppose the greatest common divisor is d. So that means that n factorial plus 1 is d times q, and n plus 1 factorial plus 1, I'll say it's d times r. Right? So d divides this, so this number is d times an integer q. D divides this, so this number is d times an integer r. So let me do some sneaky arithmetic and see if I can get a proof. So dr is n plus 1 factorial plus 1. N plus 1 factorial is n factorial times n plus 1 plus 1. Okay? Any questions about this? This is n plus 1 factorial is the product of all the numbers up to n times n plus 1. So I'm going to write this as n factorial plus 1 minus 1 times n plus 1 plus 1. 1 minus 1 is 0. N factorial plus 1, this is dq minus 1 times n plus 1 plus 1. So this is dq times n plus 1. I'm just distributing across, minus n plus 1 plus 1. This is dq times n plus 1 minus n. So
Professor,
just rearranging this, n is dq times n plus 1 minus dr. That's d times the number q times n plus 1 minus r. So d times this integer equals n. So d divides n. So d divides n factorial, which is the product of all the numbers up to n. But we're also told d divides n factorial plus 1. So if a number divides two numbers, it divides their difference. So d divides n factorial plus 1 minus n factorial, which is equal to 1. And the only divisor of 1 is 1. So the greatest common divisor of these two numbers is 1. So I'm sure there are many different ways to prove this result.
This is by induction, right? Because you
There's
said
no induction
O's.
here whatsoever. I did not
So-
use induction.
You know why I'm questioning? Because, you know, it's a direct proof. And that method is easier, the induction method, but I'm
No, I don't
saying
understand. So this is not a proof by induction. If you have a proof by induction, that's correct, that's fine. But this, what I just presented, is not a proof by induction. But this is a little bit complicated. This is not an obvious proof. So if you were trying to prove this at home, you know, you might end up spending 5 hours a day, every day for a week or two, trying to figure out how to do this. And in the end, if you are lucky, you come up with a proof which you can write down in a couple of minutes. But it does take a
Okay.
process of thinking to come up with a proof.
Professor.
Yeah,
So in this case, it will be harder to apply the theorem and like make a linear combination and find some scalars that make you give you equal to 1.
so that's a very good idea. So you're asking another way to prove this. So an alternate method would be find integers x and y such that x times n factorial plus 1 plus y times n plus 1 factorial plus 1 equals 1, right? So,
Is it hard that way?
well, I don't know. So you could do the following. If you let x equal n plus 1 and y equal minus 1, what you would get is n plus 1 times n factorial plus 1 minus n plus 1 factorial plus 1. When you multiply n factorial by n plus 1, you get n plus 1 factorial plus n plus 1 minus n plus 1 factorial minus 1. These cancel and the ones cancel. This is equal to n. So we have this relation. This equals n, which means that the greatest common divisor, the GCD, has to divide n. And if we call D the greatest common divisor, D divides n, but also D divides n factorial plus 1, because D is the greatest common divisor of these two numbers. And the only number that divides n and n factorial plus 1 is 1. So this reduces to essentially the proof I gave a moment ago. But it's because I could pick a nice choice of x and y.
So you clean up the equation, right? To make it easier for proof.
What?
So do you clean up the equation, the n plus 1 factorial? So you reduce the equation and then you prove.
Well, I didn't clean it up. This is a slightly different proof, but
Okay.
it's not better or worse than the previous proof.
Professor,
Yes.
go over the first proof,
The proof was
page
that,
89.
yeah, this proof right here.
Yeah, from the beginning.
Okay, so this is the beginning right here.
Oh, okay, okay.
All right. So you have these two numbers, n factorial plus 1 and n plus 1 factorial plus 1. And let D be the greatest common divisor. So that means D divides n factorial plus 1. So n factorial plus 1 is dq for some integer q. D also divides n plus 1 factorial plus 1. So n factorial plus 1 is dr for some integer r. So dr, that's n plus 1 factorial. N plus 1 factorial is n factorial times n plus 1. And then I snuck in a plus and minus 1. That doesn't change anything. But then I have n factorial plus 1, which is dq. So this is the same as dq minus 1 times n plus 1 plus 1. And when I expand it, I get dq times n plus 1 minus n. I get this equation, which means n, when I rearrange it, is divisible by d. So d divides n factorial, d divides n plus 1, n factorial plus 1. That's impossible. This means d divides 1. And so it's impossible unless d equals 1. So d has to equal 1. And that means that my two numbers are relatively prime.
Thank you.
Okay. Any other problems I should go over now? I will be posting online office hours. I think one tomorrow evening and one Friday morning. It's just like an office hour on campus. It means if you have a question, you're welcome to log on. It's the same Zoom login. And this is for all my classes. It could be people from other classes, just like an office hour. And
What time, Professor? This Friday?
yeah, I'll have a Zoom session tomorrow night, tomorrow evening, and also on Friday morning. I'll post the hours later today. I haven't figured it out yet.
Thank you.
Professor, can you go back to the previous slide?
You mean this one?
Yes. I got it. Thank you.
So I did not do this. I didn't find integers x and y that satisfied this equation. But I found integers x and y which satisfied the right-hand side equal to n. And then I deduced from that that the greatest common divisor had to be equal to 1. All right. If there are no more questions, we will quit for the morning.
Professor, I do have a question. So it's about the homework. So next homework due is session 1.2 and 1.3. But we just went over 1.2.
Correct.
So the homework that we have to submit is just from 1.2 and forget about 1.3 until you go over.
I'm sorry, I don't understand what you're asking.
Okay, so for the next homework, right? So 2 sessions are due in the same homework.
Yes,
We just, but you just went over session 1.2 and we're going over homeworks from this session. So should we wait that you go over session 1.3 to do that homework?
well, so the homework for lectures 2 and 3 are all problems in sections 1.1 and 1.2. There's in the second homework, there's nothing from section 1.3. If you look and see the homework assignments, the first 3 assignments are from the first 2 sections.
Okay,
Okay,